Hello. We're gonna have some fun with control structures today, and it's going to be about looping and what we call repetition. Accumulators is a big part of it. Uh, let's start off in the PowerPoint because I'm going to end up here eventually, and then we'll go have a nice conversation with Sandra and model an assignment, completing a programming assignment with loops. So this is kind of where there's some math problems that can only be solved by loops. A lot of people will initially go to the POW function like we did earlier, but the POW function does not necessarily always reflect real life with values that because the POW function zero is implied, so there's some issues there. But yeah, I've only ever done certain things with looping, and because the POW function fails quite often. So accumulators are accumulation of values and looping, being able to repeat instructions where the variables of those instructions change and then modify the repetition. That's kind of the idea. And of course, we're going to look at it because when I discuss code, I like to talk about flow a lot. And when somebody is able to see it actually happening, it's very helpful to understand what looping is and how to take advantage of it. So that'll come in when we do our modeling. Let's start off with a little bit of some structure before we start going into the weeds. So we're talking about while loops. Now there's special things in like files that you can take advantage of for reading files with repetition. And at the end of most text files, you're going to learn how to work with text files first before you learn how to work with binary files. With text files and binary, there's always an end of file character. And in fact, you can look in your ASCII code chart and you can find that EOF character. And it's automated. You don't have to write it into the file. It's automatically appended to the end when you close the file. So that's useful for reading files with repetition, so that you keep getting values until the file is done being read. Otherwise, you'd have to know how many items in the file you need to read. So yeah, repetition comes with some specific keywords with different behaviors, like break and continue statements, because sometimes when you're wanting to do repetition, you're going to want to stop repeating and not complete instructions and repeat again or continue it, so that essentially you can control in your repetition scope where you continue or you come out of the loop. That's what break and continue does. So yeah, we'll look at that too. And I think, okay, so yeah, we got a lot of stuff in here, but really seriously, walking through these PowerPoints does not give you any context. But this is an example of a loop. And in fact, let's go in and let's just actually put this in context. I'm going to pull this over here and we're going to write that code and get it so that you can actually see it. I want you to see what it does. I don't want to just go through PowerPoints where you're actually not making any connections. Okay, so there's three different types of loops. There's the while loop, the do while loop, and the for loop. The do while loop is only useful for really It's really, the do while is only useful for when you're validating input. Uh, for most things, you're going to use the while. And then I almost just say never use the do while. There's really not much use because you can do the same thing with the while. But the do while just makes validating input a little bit easier and you know, a little bit more aesthetically pleasing. So the while loop is where we're going to begin, and it works just like an if statement. So all that time that we've spent learning about if statements and scope is important because a while loop is a control structure that behaves just like an if statement. It only cares about true or false. So you can do crazy things in here like I less than 3 or I is greater than 40, and you can decide I want to repeat these instructions while I is less than 3 or greater than 40. And yeah, I don't even think that logically makes sense. But, well, I just threw those out in there, so don't try to make sense of those. Uh, but yeah, and you know, of course, you can add in, you know, the the other crazy stuff because this all gets evaluated down, and all that stuff we learned about relational operators, logical operators, all comes into play because there's only two main control structures you have. Once you learn how control structures work, they only care about true or false, and you understand how they break down into their, you know, each component part down to, you know, the last bit, which we spent time on in our, you know, previous session. This is where the hardest part because, well, you know, when working with looping to solve problems, that's when looping becomes a little bit more difficult to implement. So I got off in the weeds a little bit. Let's go ahead and just look at it very simply. And we're going to say while I is less than 0. And guys, this is the way you do looping. You start a value at 0, and that's going to be something that you use to count, possibly, or to determine when to stop looping. And you want to always have the counter of your accumulation start at 0 and go to less than the number you need. So it's going to go through 0 to 19. That's the values it's going to go through. And the reason why is because memory starts at 0. And in algorithms, if we ignore the 0, most algorithms won't work. So it's actually kind of significant. So try to set up your loops this way. You know, essentially this would be saying I want it to run 20 times. So instead of doing it 1 and then less than or equal to 20, that's no bueno. Get used to doing it like this. That's 20 times, 0 to 19. All right, and then what do we have? Well, we output I with a new line just so we can keep track of kind of, hey, what's going on here? And the way I have this set, this loop will never end. This is what we call a never-ending loop. Because I essentially never gets beyond 20. So this is what we would call a runaway loop. And it causes problems. Yes. It's, you know, sometimes a loop will run off on you and start clobbering up and grabbing all your memory. And before you know it, zoom, you no more RAM. Everything else in the machine is slowing down to a crawl. You do a Control-Alt-Delete salute. You look at your processes and you see Chrome or Firefox just blow up with the memory usage. That's what we call a memory leak. And usually they happen with loops. because, well, you can create memory in loops. And if you've got a loop that never ends, you will never stop creating memory. And machines have finite memory. They only have a certain amount. And if you go beyond that number, you're kind of off the playground. So we must watch runaway loops. Let's just for giggles see what happens with this. I'm going to control S. I don't know why IntelliSense. Oh, duh. Yeah, okay. Well, thank you, IntelliSense. I appreciate your care. All right, so runaway loop. Let's look at what happens with our flow. Now, of course, you would have other code up here, and j equals 0, that stuff would happen. Or maybe other stuff, it could be other processing, whatever. And we want to examine the loop. So I'm going to set a breakpoint at a line that is runtime. It has to be a runtime line, guys. It can't be like int j. You can't set a breakpoint here. You can't set a breakpoint on line 9 because this is just definition code. It's not runtime. So, and it's saying, well, hey, you're just defining something. You're not actually doing something on the processor. And that's where you can set breakpoints. All right, let's see, debug. Yeah, let's go ahead and start debugging. It's going to break us out right here. At least it should. There we go. All right. So now here's our flow. We've, this line got run here. Line 9 got taken care of. And we can see down here that I is 0. J, by default, I guess. Oh, J is 0. I, weird, 0. Okay, we haven't assigned I to 0 yet, but that's fine. Maybe C++ 11 autos that now. That would be cool. All right. So I is 0. While I is less than 20, output I. And that's never going to end. But you see the repetition. I'm doing step over here. Is what happens is the flow goes to the while loop. This line needs to be evaluated. And whatever nightmarish thing you got inside here is going to be determined true or false. And if it's true, then the loop continues to run. So you can actually do this. While 1. That means never-ending loop. And that's how games are built. They only break out of the loop using the break statement when you hit the escape key or something like that. So in this case, when I less than 20 is evaluated, we can see clearly when we add a watch that that is true. So it's going to continue to repeat until it becomes false. But right now, it never becomes false. In fact, let's just hit continue right now, and it will just continue this program into oblivion because we got a runaway loop. And let's just see what happens. I wonder if I can... Okay, so I really wish we could do... Let's do it side by side just for fun. Okay, hit continue. There we go. Okay, and this sucker is going. I mean, there's a lot going on here, guys. Look at that. I'm pulling it down and it's immediately going, yep, I got more output. Oh, wait, no, you can barely see it, but it's still doing it. Yeah, see? It's going crazy. It'll go until it blows the stack, which is our automated memory given to our process when it starts. So how do I stop the runaway loop? Well, simply, let's add to our accumulator, our count. And so what we can do is we can say I is equal to I plus 1. And I is going to add 1 to itself every time. You can also do this with a shorthand of I plus plus or plus plus I. Those are shorthands of doing the same thing. This is kind of the longhand version of it. Because it's such a common thing in programming, where we add 1 to a counter for an accumulation, or keeping track of how many times a loop runs, that we've got little shortcuts such as I++. So I++ is a shortcut, plus plus I. Does the same thing as this line. Okay, now when we run it, let's look at what happens. All right, good. Step over. I is 0, less than 20. Okay, and I is going up. Let's add a watch to I so we can see it happening. We can hover over it and see what it is. It's 3. Okay, so we've got the evaluation already in the watch. See, we got this I less than 20. It says true. So I is still less than 20. It's 3. So it's true. And oh my goodness, my wrist is going to kill me here. Let's do this. I'm an idiot. Let's do this 5 times. Not 20. Okay. There we go. All right. So we're going to walk it through. I increases by 1. Repeat. Should I repeat? I less than 5. True. I is less than 5. It is 1. Yes. Repeat. Continue. Should I repeat? Continue. Should I repeat? Now we get I to 4. You see where I is 4 here? Now there's a lot of these in quizzes and stuff. They will quiz you. There will be quiz questions that give you, counting loops, and it will be hard to decide whether it's a 4 or a 5, if it's -1 or +1. That'll be ambiguous. When you get those kind of questions on a test, put it in the compiler and run it on the debugger. You get the cheat sheet. Really, you do. Why not do it? You can see it. The mechanics, the inner mechanics, that mystery is the biggest problem with learning how to program. And once you uncover that, you got it. So I is 4 right now. We're still in the loop. We're going to come back for a retest. And what happened? So I was 4. It said 4 is less than 5. Yes, let's go again. Now I goes up to 5. So what we've printed so far is 0 to 4. We start at 0. We get to 4. But this is what I call, hey, where students get unsure. Does it start on 5 or before 5 with that mechanical process? So I is now 5, but the while loop has to be retested again because it hasn't been determined false yet. And this is where the ambiguity falls apart. So there. Now, I is 5. So you see down here that, and we haven't updated this part, it still says true, but that should be false. I put I less than 20 there. I was like, what the heck's going on here? Am I losing my mind? Okay, you know what? You can actually go in there and change your expression. I just threw it in I less than 5. So now it just says, oh, that's false. You see what I did there? I just kind of went in there and changed that watch. Yeah, it's cool like that. So yeah, I is less than 5 is false now because I is 5. So then that means, oh, we're no longer going to loop. It's time to stop. And what does it do? It continues the mechanical top-down behavior, but not within the scope of the while loop, because in that scope only runs, that code only happens. In fact, if I defined an integer in here called k, I can't access k after or before because it's only available in the scope of this loop that starts here and ends there. Just like this function scope starts here and ends there. So think about those scopes as your memory and your runtime. Your runtime from top down and your memory allocation from top down within that scope. What's cool though is I is available. because I is at function scope. So I can mess with I all I want, as we just did. So yeah, I would have an error out here if I just decided to do k is equal to 0. Because it's going to complain, I don't know what k is. And you see the little squiggle there? If we try to compile it, it'll just give us a little bit of an error. Oh, I messed up. Okay, k is undefined. Okay, let's reduce this to 3 and let's look at the mechanics one more time before we move on. All right, we go in, boom, k is created. It's not available anywhere but within this brace and this brace. Okay, I is now 1, I is now 2, I is now 3. So I less than 3 is going to be false. I less than 3. There we go. It's right there, false. So your runtime is going to go down here. Okay, and then it just, what it does is it just, you know, we can put some statements here, you know, and it'll just go down to there and complete those statements, you know. So then your runtime goes down here and it'll do this. And then it'll go down to your next statement. So that's what, you know, control structures. We control the flow. And so we can repeat the flow. And that's how we solve a lot of problems, computer science. A lot of algorithms are built this way. All right, when I get back, you guys might want to take a little mini break. I'm going to take a little mini break. And when I get back, I am going to talk about the continue and the break statements. Okay, now the continue and the break statements are a very useful tool. Let's talk about the continue statement, because the main purpose of a loop is to solve a problem. And what we would want to do that is, speed is always brain power, and it'll never change. If somebody is able to do a job faster than somebody else in the, you know, like, oh, let's think about it as, you know, streaming video and decoders and coders to make it faster to transmit video over the internet. If you can do that algorithm faster, that's money. It's just, you know, you can print it, essentially. So speed is always important. And what the continue allows you to do is solve, you know, in your flow, if you solve a problem at the beginning of your while loop, let's say that we have, you know, we have a problem that we're trying to solve, and you know, hey, maybe we got some code in here, you know, whatever, j plus 1. And by the way, never declare an integer like that. If you need it, it's got to be up here. It's got to be up to the top. Okay, so let's say that we solve the problem in line 14, and we don't need line 15 and line 16 to run because it's inefficient and we want to be faster in our algorithm. So what we can do, but the algorithm loops. It's an infinite loop of maybe video streaming until the video is done streaming, and you want to just continue back to the next loop to solve the problem again with different data. And so what you can do is you can go to that next iteration faster than you would otherwise. So let's say that I solve the problem on line 14 and I don't want the loop to get to 16 and 17, but I still want it to loop because it's a video and it's the user that stops streaming it. You know, maybe it's broadcasting something. Solve the problem, go back to your iteration to solve the next problem. And the behavior of it is essentially your runtime skips over these guys, comes back up here to continue on. So usually you'll have the continue within some kind of if statement. This is just demonstrating what it does, its behavior with your flow. So you would have some kind of decision making on whether to continue or not. So the continue would be embedded inside the scope of an if statement. Okay, let's look at behavior. Okay, we start here at line 10, skip over. I is less than 3, okay, good. Then we do our line 14. We solve the problem. Then we say, oh, the problem solved, continue. Now you're going to see that the runtime is going to skip 16 and 17 and go right back up here to 11. Okay, now the way this is written, lines 16 and 17 never get to, or never gone to. So that's the danger of continues. That's where they can get dangerous and cause problems. Like you put a weird continue somewhere on one version, and before you know it, you've broken everything because of that behavior and some weird logic or whatever. You know, continue statements often bite you in the butt. They do. So they're often, you know, only if j is greater than 5. Do we want to continue? And then what it'll be doing is the continue will only happen when j is greater than 5. And that's the only time these lines will be skipped. So that's the kind of setup you would normally have with continue. Now break is the opposite. Break is, and let's pretend that we have a runaway loop. Let's say that we're building a game or something. And let's say that when a value like j reaches a certain point, and let's say that when it gets greater than 5, we stop the game. The game's over. We come out of the rendering loop or whatever. And so what this does is break allows you to come out of the whole loop. And it's between using continue and break that you have control over regions of your loop, your repetition body. It's actual in the scope of the loop. And it's very useful in a lot of ways for creating efficient code. Efficient code, mostly, in a lot of ways, yeah. That's what they're used for, efficient code. Of course, this is very inefficient, but that's what games are. They're just a continuous loop that never ends until the user or the game decides to stop. And then you get the break statement and your game pops out. It's done and over. Or that section of the game or part of the game that's looping. So let's look at what happens with our flow. Okay, we step over. We have a loop. Okay, we never get to that part yet. We've got to wait until j is greater than 5. Okay, we're not breaking yet. J is now 5. It's not greater than 5 yet. Oh, wait. Oh, I was watching I. Excuse me. J was. Yeah, I is 5. J was greater than 5. I guess evidently that's where it got 6. Okay. I was off by 1. Oh, no, I was off by a whole variable. Excuse me. Yeah. All right. So step over. This is the break. It's going to execute. And boom. It immediately takes the runtime out of the loop. No more loopy. And then you go down to, your runtime goes down to the loop is complete and you continue on. And this would be where you would shut down the game or whatever, or, you know, whatever you needed to do when that loop was done running, that iteration process. And so that's what a break is used for, is just to, it's kind of like, stop looping, let's get on out of here. That sort of thing when you know, for your runtime. um, hmm, I think let's get back into some PowerPoints and see kind of, because there's another loop that I want to cover. It's the other more important loop. I'm gonna leave the do while up to you guys. We're gonna talk about the for loop, but let's see and make sure that we're kind of moving in the right direction. We got some modeling of that. Okay, yeah, that's good. Less than n. Yeah, we demoed that. Sentinel. Oh, Sentinel. Okay, a sentinel is a variable that's used to keep track of whether you should loop anymore. It's not like a counter. It's a different type of uh, decision maker for deciding whether to continue to loop or iterate. And a sentinel will be maybe a flag that's probably maybe set somewhere else in your runtime, your flow, or it could be a user input that's inside of the loop. And in this case, that's how it's using it. It's using the sentinel that's preset and something that the user enters to see and test whether the loop should continue. All right, and so that's, you know, sentinel controlled. A Boolean controlled is one where you can, you know, of course, since a while loop only looks at bool, you can directly pump one in there. In fact, when I put the 1 in there, that was essentially throwing true. That's what I was doing here, while 1. That was essentially doing this, true, while true. Because the while loop only cares about true or false. And guess what true is? True is the number 1, false is the number 0. For every language, it doesn't matter. But for every language, we have a specific way of doing Boolean with the words true and false. So I'll shortcut some of that. Okay. See where else are we? Okay. Oh, that's good. I like that. The random. That's interesting. Let's talk about random real quick. Now, a random integer can be any number between 0 and 32,000. Actually, I think integers, an unsigned integer is 0 to 64,000 or something like that. And this is a short int, not a regular int. A 4-byte int can get a little bit higher in value. So they're talking about the short 2-byte int. But when we use the random, we can randomize a large number between 0 and 32,000. But what if we need to bring that random number between 0 and 100? So we can get a random value, but that's what a modulus does. And a modulus is pretty much the most important, one of the most important operators in computer science. And in fact, let's actually take some time to demo that, and then let's see. We need a special tool for rand to include in the library. And let me make sure. I believe it's we got to seed it. Yeah, standard lib. See standard lib. Okay, now the thing is with random numbers, for it to officially test the Gaming Commission, if you're doing a digital game, you have to seed it with a value, a unique value. And the best unique value to seed it with is the epoch value. Now, the epoch value is a very important number in computer science. And basically, it's how computers keep track of time. And basically, oh, yeah, epoch value. Essentially, computers keep track of time with one number. One huge number is your timestamp. And with that one number, you convert it to months, days, year. Uh, and that number is based on milliseconds from the first BIOS in the 70s. Yeah, crazy. That's how computers keep track of time. And so that's always going to be a unique number because it's always counting up. And this is the epoch value currently now for time. And you'll see in a lot of logs, if you want a timestamp, they just give you the epoch number. You know, if you know, let's say that somebody visited a website they shouldn't have, and you look into the logs, they're going to show the website and then a number like that as the timestamp, and then you got to go in and convert it to, you know, what time and what date that happens. So that's always a number that we can use that's unique to seed our random. Okay, now we're going to seed our random. And you know what? We're getting off the rails here, but your PowerPoint is the one that started on. I wanted to do four loops, but that's okay. Let's do this real quick, and then we'll get into for loops. C standard lib, and then we'll probably blast through whatever's. I probably won't be able to get to everything. C standard lib, CST D, yeah, I forgot the D. Okay, now that's where rand comes in. Now if you adjust, and let's do this, if you were to just output random numbers, and let's say let's output 20 random numbers. And let's do rand, the rand function. Let's do this. Let's do j is equal to rand. I think I might need to look into that, but then we're going to output j. And so we're going to output a random number 20 times. Let's look at the behavior. Okay, step over. We use the rand function from the C standard lib. The standard library is usually, you know, what we call it. And let's see if we got a working value. J, you can hover over, it's 41. And then it continues on, and we get another random number. Now here's the thing, is often if you do things this way, you're not going to be truly getting a random number. It's going to fail. But depending on how you use it, sometimes it works out right, but the way you're supposed to use it, where it doesn't fail, because I've used rand in different situations, and it totally just gives me the same number over and over and over again. It's horrible. So essentially what needs to be happening here for it to pass appropriate randomization is to seed it. And you do that with this variable. Not variable, it's a function, time. And we're probably going to have C time for that. And what this outputs is just essentially epoch in milliseconds. That's all it does. And you know that website I showed you was showing you epoch in seconds. So the number gets actually bigger when you're actually using it, because it's not seconds, it's milliseconds from the 70s. So we're missing a couple zeros there. Okay, you're going to see that when we output it, at least I hope. Okay, let's run it and just look at the output. Okay, you see that big long number? So we did it 20 times, and what the heck? It's doing weird things. Interesting. Yeah, those results were a little screwy. That's because of this guy right here. I was being silly. Let's get rid of that for now because we're heading into now. Apparently, I was wrong. Time actually returns time of zero. Actually returns seconds. Uh, you can get milliseconds though. It's there. I believe you get. I believe you got to use the chrono library for that one though. Let's see. All right, let's look at output. Okay, that's more like it. Okay, so it's good to seed with this number, but it's better to seed with milliseconds. So actually you would use this code, but I'm getting it, you would use the chrono epoch time, now time since epoch. We're getting in the weeds. Let's move on. Seconds is fine enough, just enough for you guys to know that you should be seeding with a millisecond time. So how do we seed? And there's actually a function for that. And I believe what is it? Yeah. Okay. Yeah, I'm referencing this again. There we go. Okay, and it wants a cast to int. Okay. So this is the proper way to seed. And you would do it before the loop. You would call srand, seed rand. And it's a function. Now all it needs is time zero. So if I'm gonna hack this, I would just do time zero. I would do time zero, and then I would just throw an int in front of it instead of the full on int static cast. But essentially it's just taking that number, converting it into a friendly integer for srand, for the seed rand function. Yeah, whatever. And once that happens, then we would get some decent output when we call the rand function, or when we print j. Something a little bit more uniform and random, and that's the proper way. But what if we wanted to constrain these values, because those are big numbers, and what if we wanted to say that hey, while j is I don't know, less than 20, or, and I'll fix the lot. I'll fix it. J is greater than 80. We'll fix the logic and play with this later. J is equal to a random number. And let's say that we are creating a game where somebody rolls a 0 or a 50, a number 0 to 50, they lose. And J is what they're rolling, the dice that they're rolling, or whatever number they're being assigned randomly. And if it's any other number constrained between 0 and 100, then they win. So how do we constrain it, that big, large number between 0 and 100? Well, let's not mess with this yet, because that's just, how you would do it, or why you would go about it, different things like that. But let's just look at the mechanics. And let's say that we're going to randomize J with, it's already been seeded. And we're going to take J, and we're going to say J is equal to J modulus 3. And that's what this operator is called, modulus 3. Okay, what is modulus? It's the remainder of. And how does that work? Well, it's integral. It works. It's a special integral behavior that we have to scale things down or to take an accumulation and break it up into smaller pieces mathematically. So let me show you how it works. Right now, we're throwing in J mod 3, and we're going to have a condition based on J, some kind of condition. But oh, look at all my scribbles. Ooh, not bad, not good or good. Okay, I'm gonna try to do best. Do good. Okay, so let's say that we have X being the answer, and then J being the counter, or actually, you know what? This would be I because we're using I as the counter, not J. So we're going to be using I here. Let's do this. Control Z because I messed up. Okay, good. So we got an I here. That's our iterator, and we're going to do J is equal to I modulus 3. That's a 3. No, it's not. That's a 3. Okay. So J, each time through the counter in the loop, I is going to continue going up to 20. I in the loop is going to go all the way to 20. So we want to see what happens to J when I is 0. X was a bad idea. That's J. When I is 0, 0 mod 3, we're saying take 0, divide it by 3, and what's the remainder? Well, that's easy. 0 divided by 3 is 0. So its remainder is 0. Now, things get interesting here just first. It might be confusing, but you'll see the pattern eventually. Because this is all done with integers, there is no floating point values. So when you take I of 1, when I is 1, and you say, what is 1? What is the remainder of 1 divided by 3? And since 1 divided by 3 is 0.33, it goes into nothing zone. We say that the remainder is 1. Same thing as 2, because we only have integral answers. So 2 divided by 3 is a nothing burger, and the remainder is 2. Now here's where it gets interesting and the confusion dies. When we have 3 divided by 3, when I is 3, three divided by 3 is 0 with a 0 remainder. Okay, now what happens when I goes to 4? 4 divided by 3, well, how many times does 3 go into 4? 3 goes into 4 once. And what's the remainder? 1. 3 divided by, or 4, yeah, 3 goes into 4 once with a remainder of 1. So 4, when I is 4, it's 1. Okay, what about 5? 3 goes into 5 once with 2 left over. Okay, 6. 3 goes into 6 twice with 0 left over. Okay, so we got 5 is what? 2. We got 6 is 0. Okay, when I is 7. 3 goes into 7 twice, because you get 6. 3 times 2 is 6, with a 1 remainder. Do you see the pattern yet? So no matter how big the number gets, If we do a mod 3, we're going to always be able to bring it to a range between 0, 1, and 2, between 3 numbers, mod 3. If we did a mod 4, it would be 0, 1, 2, 3. We would have a range of 3 numbers. So it would be 0, 1, 2, 3, 0, 1, 2, 3. That would be mod 4. Mod 5, the same thing, but 1 up. And so that's how we can break down iterations into different parts. Modulus really works well for a lot of things in computer science, a lot of things. So if I were going to take the random number generated here and I wanted it to be between 0 and 100, I would do as j mod 100 plus 1. And that would take it from 0 to 100. So my modulus will be mod 101. That would give me the 0 to 100 values that for my modulus values. So now look at it. Oh my God, what did I do? Oh, I got a never-ending loop. Let's do j is less than 100. And this would be a game, you know, maybe 100 rolls, and you would say, okay, you rolled a 65, that's greater than 50, you win. You rolled a 9, that's less than 50, you lose. That sort of thing. And you can put the operators with that to look between a range with an OR operator, and then, you know, mix them up with ands and stuff like that. Okay, that was a little bit of a side journey. Thank you, PowerPoint. We're not going back to PowerPoint until the very end. Make sure there's comment because this is getting too long. And I'm going to concentrate on vital data. This was pretty vital, actually. But here's the last loop that we're going to talk about. This is where everything's controlled. If you notice in this loop, we have a starting value. We have an ending value. And we have a counter. Those three things. Starting, condition, you know, starting, stopping, iteration. Because we can do, hey, how many times does this loop run? And you would say 100 times. But what if I do I is equal to I plus 2? How many times does it run? 50 times. But wait a minute. Does it start at 0 and less than 100? Where does that? It gets complicated. That's where you just get into debugger and just play with it. And use it like a calculator. It's wonderful. You can use it for so much. It's the best calculator in the world. The best cheat sheet in the world. So let's do 4. So those 3 things. Start, continue, stop. Continue meaning iterate. And then when do we stop? Start, stop, iterate. Start, stop, iterate. You need those 3 things for a loop. And those 3 things are brought together in what we call a for loop. And the way a for loop is designed is you have to plug in those 3 things. And so therefore a for loop is the safest loop that you can use. And essentially I say use it for everything that you can. There are times where, you know, a never-ending loop, that's a while loop. But a for loop for everything else, that's the way it should be. So, start. Well, we need a variable for starting. Now, we can use I here, or we can use a variable that we create inside of the scope of this guy. So, I is traditional, but we don't want it to mess with anything else. So it's customary to just say int I here. And it's going to be created within this scope. So that I is not accessible out here or out here. That's custom. You want to do that. Because you want to control the variables or always have, I mean, because it's so common to have for loops that everybody starts with I and then goes to J and then therefore for other nested loops, which you can have nested loops. So you can put another for loop in here or a while loop. You can have a loop inside of a loop. This is a start. Okay, I equals 0. This is my counter. Okay, let's say that then how am I going to stop? Well, I'm going to say we're going to go until I is less than 100. That is your stop. Start, stop. Okay, now how are we going to iterate? How is that going to happen? And that's your iteration. And there you can just do I++. It's the same thing. You can do I is equal to I plus 1 here. That works. C++ is crazy like that. It'll evaluate it. But it's customary to do I++. And the syntax of this between those three important things is very purposeful. You see that they're semicolons. That's what delimitates them, and it's only useful for a for loop. Okay, now let's look at the counters and then behavior. So we can do a cout I, and let's have some fun with this. Let's say if I modulus 3 cout, and I'm only going to do a one-liner, so it's going to be in the scope of the if statement, and that's when we're going to input a new line. So I is going to start at 0, it's going to go to less than 100, and it's going to iterate. So this is our controlled loop. Let's look at our output first. Oh, what did I do wrong? We don't really need that. I think, oh, I didn't save. Make sure you always save before you rebuild. That's like such a common error. No, something's wacky. Oh, duh. Oh, the news just popped up. Yeah, we need to put some spaces here so it doesn't look weird. That's kind of the issue here. Okay, let's put a space there so that we print numbers. And then when I becomes a multiple of 3, we do a new line. So we'll have 3 numbers, new line, 3 numbers, new line, 3 numbers, new line. Now we're going to have an off by 1 issue here. Because you see, evidently, we got 2 numbers. 0, 1, 2, 0, 1, 2. Oh, it's my logic. Sorry guys, I was definitely not there. Okay, well, we need to apply this I mod 3, because what I want is every time a 0 happens, or in this case, we got 0, 1, 2. So every time a 2 happens, we do a new line. Because we got 0, 1, 2, new line. 0, 1, 2, new line. Okay. Good. So this is 100 numbers with a little bit of some context on some of the use of modulus. This is just a taste, guys. I can talk for days, hours on programming. But we're at an hour, and I don't want to, I want to, we're going to continue with a demo. It'll be another video, so expect that. Paired with this one, we'll go ask Sandra for a programming problem and then hack it out. Okay? Yeah, I don't want to get off track in the PowerPoint, the rest of the PowerPoint. We've hit the key points. I've talked to you about context a little bit, and of course, you know, the big kahungas, which is the looping. That that's the big kahungas. There's some other stuff in there that I'm going to leave up to you guys for your reading and your play time. Okay? All righty, guys. Take care. Bye.